All right, everyone. Let's get started. The schedule for this week is we do the practice sessions for chapter 4. Okay. So these are the questions we are going to review together. Okay, let me write down this question first. Okay. So in chapter 4, we discussed different type of distributions, like Bernoulli distribution, binomial, Poisson distribution, and then of course normal distribution. Okay, and then at the end of this chapter, we discussed central limit theorem. Okay, so the first question, page 202, question number 2. Is here. So a certain brand of dinnerware set coming in 3 different colors. Okay, so we have red, white, and blue. So 20% customer order the red set, 45% order the white, and 35% order the blue. Okay, so 20% plus 45 plus 35. So that's 100%. So the color are 3 possible outcomes. So we have blue, red, and white. So let x equal to 1 if a random chosen color is a red set, and x equal to 0 otherwise, and y equal to 1 if the order is white, and otherwise y equal to 0. Could you mute yourself, please? Okay. So z equal to 1 if for either a red or white. Okay, so z equal to 1 if it's either a red or white, and z equal to 0 otherwise. All right. So A, let Px denote the success probability of X, and find Px. Okay. So this is question number 2. So Px success rate for X. So X equal to 1 if the color is red. Okay. And from a question, 20% is red. So very easy for Px is equal to 20%, or 0.2. Okay. B, Py denote the success probability for Y, find Py. Okay. So again, Y is equal to 1 when the order is white. Okay. And we have 45% of the order is white. So Py will be 45%. Okay. So that's easy. C, Pz is success probability for Z. Okay. So Z equal to 1 if it's either a red or white. Sure. So either red or white. Okay. So for white, the probability is 45%. And for red, it is 20%. So it's 0.2 plus 0.45. So that is 0.65. Okay, so the color could either be white or red. Okay, if z equal to 1. Okay, so that is 65%, right? Okay. So far it's easy. D, is it possible for both x and y equal to 1? So for x equal to 1, when the color is red. Okay. So x equal to 1 when it is red. And y equal to 1 when the color is white. Okay. So is it possible for both x and y equal to 1? Okay. So that means the color will be both red and white. Okay. So that is impossible. Okay. So not possible. Okay. So for D, the answer is no. Okay. Because we cannot have the color to be both red and white. That's part D. And we also see, because the color can either be red or white or blue. Okay, so there's a no intersection between x and y. So that means intersection of x and y equal to 0. Okay, so that means x and y are exclusive to. Part E. Okay. So E is asking, is it PG equal to PX plus PY? Okay, so PG is, we answer from part C, it is 0.65. Okay, and PX is from part A, 0.2, and PY is from part B, it is 0.45. Okay, so it turned out, yes, PG is equal to PX plus PY. Yeah. Part F is a little interesting. It's asking, does Z equal to X plus Y? Okay, so how to answer this part of question? Okay, so that is, we should check all the possible scenario and check if Z is equal to X plus Y. Okay, so for this question, this is about color. We have 3 possible outcomes for the color: blue, white, and red. And we should check for each of the 3. Okay, so the first one, if the color is red, okay, and then let's check X, Y, and Z. So if color is red, X is equal to what? X equal to 1, because X is equal to 1 when the color is red. Okay, and Y equal to what? Okay, so Y equal to 1 when the color is white. So when the color is red, Y will equal to 0. Okay, so Y equal to 0. Okay, and then look at Z. So Z equal to 1 when the color is either a red or white. So when it is red, Z will equal to 1, right? So Z equal to 1. So when the color is red, X plus Y equal to 1 equal to Z. So in this part, Z equal to X plus Y. Okay, so that's one of the 3 scenarios. Then similarly, we check the next color. When the color is white, okay, then X will equal to 0. Okay, because X equal to 1 when the color is red. So X equal to 0. And Y is equal to 1. Okay, so Y equal to 1 when the order is white. Okay, and Z is also equal to 1. Okay, so z equal to 1 when the color is red or white. So again, when the color is white, we found out z is equal to x plus y. Okay, check. And then we check the third of the three scenario when the color is blue. So when the color is blue, okay, x will equal to 0. Okay. So x equal to 1 when the color is red, otherwise s equals to 0. Okay. And y is also equal to 0. Okay. Because y equal to 1 when the color is white. For other color, y equal to 0. And z, same thing. So z is equal to 1 when the color is red or white. Okay, otherwise it is 0. So blue, z equal to 0. So in this scenario, z is also equal to x plus y. So for all the three possible scenarios, z always equal to x plus y. So we can conclude that z is equal to x plus y. Okay, so again, we need to check all the three possible scenarios. Okay. So that is first part of the question. Question number 2. And then question number 6. Question number 6. So 2 dice are rolled. Okay. So we have 2 dice. X equal to 1 when the dice come up with doubles. So that means, we have 2 dice. Doubles means we have 1, 1, or 2, 2, or 3, 3, or 4, 4, or 5, 5, or 6, 6, right? So we call that double. So same result for the 2 dice. Okay. And x equal to 0 otherwise. And y equal to 1 if the sum is 6. Okay. So we have 2 dice. Okay. Okay. So y equal to 1 if the sum is 6. So for example, the first dice is 2, the second is 4. So 2 plus 4 is 6. So the sum is 6. So y equal to 1. And otherwise, y equal to 0. Okay. And z is equal to 1 when the dice come up both doubles and with a sum of 6. Okay, so that is only one scenario. So we have double 3. So we have double 3, it is double, and the sum is 6. So satisfy both x and y. So z equal to 1 when we have double 3. Otherwise, z equal to 0. Okay. So first of all, before we calculate the probability for x, y, z, let's do the counting method. Let's use the counting method to count how many possible outcomes and how many of them are doubles and how many of them are the sum of them is 6. Okay. So we have 2 dice. We can think this as a 2 steps experiment. So the first step, we see the number for the first dice. We have how many possible outcomes? 6. Okay. So the first dice is the first dice. Okay. So possible outcomes is 1, 2, 3, 4, 5, and 6. Okay. And the second step is number for the second die. Okay. So then, how many possible outcomes? Okay. So when the first one is 1, the second one could be 1, 2, 3, 4, 5, and 6. And for second, when the first one is 2, we also have 6. Okay. So 1, 2, 3, 4, 5, 6. All right. And same thing for 3, 4, 5, and 6. Okay, so how many possible outcomes totally? Okay, so that's 2 steps. The first step, we have 6 possible outcomes. And then for each of the 6 possible outcomes from the first step, we also have 6 outcomes. So that's 6 times 6 equal to 36 possible outcomes. Okay, and then let's look at x. So x equal to 1 when the dice come up doubles. Okay, so for x, the sample space will be, we have 1, 1, we have 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Okay, so that is x. Okay, so we have a doubles. Okay. Then for y, it is defined the sum is equal to 6. Then how many outcomes for y? Okay, it will be when the first one is 1, first die is 1, the second one will be 5. Okay, this one, 1 and 5. Okay. Or when the first is 2, the second one is 4. So 2 plus 4 equal to 6. Okay. And when the first is 3, second one is 3. When the first one is 4, second one is 2. First is 5, second is 1. And anything else? When the first is 6, the second one will be 0. Okay, that's no 0. So we only have these 5 possible outcomes, right? So 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. Okay, so that's first and second die together. Then we can look at the answer. For part A, so Px is success property of X. Find Px. So for X, we have 6 possible outcomes. Okay, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. So that is, so Px equal to 6 over the total. Right, the total is 36. Okay. So it's 1 over 6 for Px. Part B, so Py is success property for y. Okay, so y is when the sum is 6. Okay, so for y we have 1, 2, 3, 4, 5. Okay, so Py is equal to 5 over the total of 36. So that's Py. And part C, okay. So Pz is success property of Z. Okay. So Z is equal to 1 when the dice come up both double and with a sum of 6. So that is double 3. So for Z, we only have one possible outcomes, which is double 3. And that's it. So PZ is equal to 1 over 36. 1 over 36. And let's look at D. All right. So D is asking are X and Y independent. Okay. So if X and Y are independent, then so this will satisfy. So if X, Y are independent, then Px times Py will equal to Px and Py. Okay, so the half circle facing down is and. So we're going to check if this equation satisfies. Okay. So Px and Py. So when x equal to 1 and y equal to 1, that is double 3. Okay. So this part is double 3. The chance for that is 1 over 36. Okay. And for Px, so Px is 1 over 6, as we see from here, part A. And Py is 5 over 36. Okay, so we check Px times Py is not equal to 1 over 36. Okay, so we will see they are not, X and Y are not independent. Independent. E, so E is similar to D. So E is checked if Pz is equal to Px times Py. Okay, and for Pz, it is 1 over 36. Px is 1 over 6. Py is 5 over 36. Okay, so it is not equal to, so Pz is not equal to Px times Py. Okay, so the answer is no. Okay. So the last part of this question is a little interesting. It is asking, is z equal to x times y? Okay, so for z, we could have 1 or 0. For x, we could also have 1 or 0. Same thing for y. Okay, we should check for all the possible scenario if z is equal to x times y. So the first scenario is when the dice come up with a double 3. Okay, so that is when z equal to 1. The only possible way z equal to 1. So when the dice have double 3, double 3. Okay, so when it is double 3, let's check x. Okay, so x is defined, the dice come up with doubles. Okay, so when it is double 3, x will equal to 1. Okay. And y, so y equal to 1 when the sum is 6. Okay, So when we have a double 3, 3 plus 3 is equal to 6. So y, yes, equal to 1. And z is equal to 1 when it has double 3. So z equal to 1. So in this scenario, we checked z is actually equal to x times y. Check. Okay. And then when dice doesn't have a double 3, so not have a double 3. Okay. And then for z, okay, z equal to 1 when he has double 3. Otherwise, z equal to 0. So when it's not double 3, z will equal to 0. And then, right, so when, for all the other possible outcomes, when it's not double 3, then either x or y, or both x and y equal to 0. Okay, so that means at least one of x and y will equal to 0. Okay, so let's say either x or y or both x and y, okay, equal to 0. Okay, so as a result, x times y will equal to 0. So this is actually equal to x times y equal to 0. Okay. So for all the possible scenario, z is actually equal to x times y. So always true. So that's part F. All right, so for this question, we use counting method and we count how many possible outcomes for different situation. Okay. And this question number 6 here. Next question is question number 2 from page 212. All right, I think that's section 4.2. Okay, so here. Question number 2. Question number 2. Okay. So x follow binomial 9, 0.4. Okay, and find different possibility. Okay, so binomial has 2 parameters, and both parameters tells us. Okay, so binomial NP, the probability max function, so Px is equal to this. Okay, so that is a probability max function for binomial NP. Okay, binomial distribution, again, it is we have n Bernoulli trial. Okay, and for each trial, the probability for success is equal. For example, we toss the die 10 times, and each time we have success, for example, we have tail. If we define tail is success, then success probability is 0.5. Okay, so in that case, it would be binomial 10, 0.5. Okay, so remember, so binomial is for experiment in that case. So the question tells us is binomial n 9, 0.4. Okay. Then we just simply plug in the number in the mass function here. So for p x equal to 6, sorry, not equal, larger than 6, larger than 6. All right, so that is equal to p x equal to 7. Okay, so 7 larger than 6, or px equal to 8 plus px equal to 9. Okay, anything else? Could we have x equal to 10? We cannot, because we have 9 trial. So the most number success happen is 9. We cannot have 10 success, right? So px equal to 9 is the max possible. Then the next is we just plug in x equal to 7 into the mass function here. Okay. So 9 is the n, p is equal to 0.4. Okay, so we just do the first one, px equal to 7, that is n, factor of n, so that is factor of 9. Okay, factor of x, so x equal to 7, so it's factor of 7, n minus x, so that's 9 minus 7, factor of that. So times p is 0.4, x to the power of x, so 7. 1 minus p, 1 minus 0.4, n minus x, so 9 minus 7. Okay, so that is for px equal to 7. Okay. Similarly, we plot x equal to 8 and n equal to 9, p equal to 0.4 into the mass function here. So we do same thing here and same thing here. Okay. So to save us time, I will not write down the same thing. Okay. Again, when you do the homework or do the midterm or final exam, you can use your calculator to tell your calculator to do this calculation. Okay, you don't have to do all these details yourself. Okay, for some of the calculator, you can tell it is followed by binomial n and p, and you can tell n equal to 9, p equal to 0.4 for this case. And if you calculate px equal to 7, it will give the answer directly. Okay. So any question about how to calculate this? Okay. All right. So px larger than 6, including x equal to 7 plus 8 plus 9. Okay. The next part for px larger or equal to 2. All right. So that is a lot of calculation, right? So px larger or equal to 2. So what we can do is we can just px equal to 2 plus px equal to 3 plus px equal to 4, blah, blah, plus px equal to 9. Okay, so that is many calculation. Okay, or we can use the fact that all the probability for mass function added together is equal to 100%. Okay, so based on that, we can kind of simplify that. So px large or equal to 2 is equal to 1 minus px less than 2. Okay, because px larger than or equal to 2 plus px less than 2. So that is all the possible probability added together. So that is equal to 100%. Okay, so this is a trick you will often use for probability mass function. Okay. So that's equal to px less than 2. So less than 2 including px equal to 0. Okay, don't forget 0. 0 means we have a 0 success out of this 9 trial. So do not forget x is possible to be 0. So px equal to 0 minus px equal to 1. Okay, and do not include px equal to 2 because this is less than 2. Okay, do not include px equal to 2 here. So just this. Okay, and then what we do is we plot x equal to 0 into this mass function here. Okay, n equal to 9, p equal to 0.4. Okay, same thing. I will not repeat. Then you get the first two correct. The remaining will be very much similar. Okay, just pay attention to the equality line here. So part C is for x large or equal to 2 but less than 5. Okay, so that is including px equal to 2 plus 3. Oh, sorry, there's no equality line here for 5. So that's okay. Plus px equal to 4. Okay, no 5. Okay. That's part C. Part D is similar. Okay. So larger than 2, but less or equal to 5. So that is px equal to 3. No 2 here. Plus 4 plus 5. Okay, that's 5. E, so px equal to 0. Okay, so you just plug in the number into the mass function here. Okay, I will just skip this. Right. EF, so F the same thing, px equal to 7. Okay, and mu x for G. So mu x for all the binomial distribution, the mu x is equal to np. Okay. So n is equal to 9, p is 0.4. So 9 times 0.4. And the h, so for all the binomial distribution, variance sigma square is equal to np times 1 minus p. Okay. So n 9 p 0.4. Okay. Right. Before the exam, to save you the time, you can just write down for binomial distribution, what is the px, what is the mean value, and the variance for binomial distribution. And same thing for Poisson distribution, and also normal distribution, of course. So that's question number 2. Okay, we are here. Question number 4 is the next. It's here. So at certain airport, 75% of flights arrive on time, and a sample of 10 flights is studied. Okay. So we have 10 flights, and for each flight, the probability arrive on time is 75%. Okay. So that is a classic binomial distribution. A, find the probability that all 10 of the flights were on time. So if X is defined as number of flights in a sample that arrive on time, okay, so X is number of sample on time, then X will follow, you should write this down, binomial NP, N is 10, P is 0.75. Okay, 0.75 is the probability for each flight arrive on time. Okay, so this is very, very important first step. You define what distribution your experiment follows. Okay, then the remaining will be easier. Okay, so A, all 10 flights are on time. So Px equal to 10. Okay, we use the same max function here. Okay, factor of n over x, factor of x. Okay, so that is equal to factor of 10, factor of 10, 10 over 10 minus 10. So n is equal to 10, x is also equal to 10. Okay, p is 0.75, n is 10, 1 minus p, and minus x, 10 minus 10. Okay, so it turned out when all the 10 flights arrive on time, the probability is 0.0563. So around 5.6%, all the 10 flights will arrive on time. Okay, so very small chance. B, very similar. Exactly 8 of flight were on time. So that is P x equal to 8. Okay, so again, what do we do? I think everybody knows this. We plug in n equal to 10, right? X equal to 8, P equal to 0.75 in this equation. Okay. This equation is the mass function for binomial distribution. And I will just skip the details for Px equal to 8. Part C, find the probability that 8 or more on time. Okay. So 8 or more is Px large or equal to 8. So that is equal to Px equal to 8 plus 9 plus 10. Okay, so 10 means all flights arrive on time. That's no 11. Okay, it's not possible. Okay, so 8, 9, 10, add it together. Okay. So that is question number 4. Questions so far for this? Okay. The last question for binomial distribution is question number 6. Okay. It's here. So a fire die is rolled 8 times. So fire die means the chance it has a head is 50%, same as it has a tail. Okay. We call that fire die. So roll 8 times. Okay. A, what is probability that a die come up 6 exactly twice? Okay. So first of all, let's define X is the number of times the die has a 6. Number of times die shows 6. Okay. All right, and then X will follow a binomial distribution. Okay, and P. Because why? Because we toss the die 6 times. Not 6, 8 times. Okay, and each time it has head, it has a 6 will be the same. Okay, so n is equal to 8 times. What is p here? Okay, so for fire die, sorry, it's a die, it's not a coin. Okay, so fire die, the chance it show a 6 is what? 1/6, because the die has 6 faces, right? The chance it show a 6 is 1/6. Okay, so p here is 1/6. P is 1/6. Okay. Then the part A, what is probability the die come up 6 exactly twice? Okay. So part A will be asking Px equal to 2. Okay. So that X actually not equal, follow binomial 8, 1/6. Okay. So Px equal to 6. Again, plug in the mass function. N equal to 8. X equal to 2. N minus X. P 1/6. X equal to 2. 1 minus P. N minus X. Okay. So 0.2605. So the chance the die come up with the 6 exactly twice is 26%. Okay. So let's look at part B. What is probability that the die come up an odd number exactly 5 times? Okay. So that's a different experiment. So this is talking about odd number. It's not come up with the 6. Okay. So let's do another define. So let's define y. So y is the number of times the die come up odd number. Odd number. Okay. So y will follow again binomial. N is 8. Okay. So what are the chance it show an odd number for the die? P. What is P here? Anybody want to have a guess? It's very straightforward. So for fire die,
y minus 5.
the probability the die shows odd number. Odd number is 1, 3, 5. Correct?
1/2.
1/2, because we have 1, 2, 3, 4, 5, 6. So 6 phase, and 3 of the 6 phase odd number, which is 1, 3, and 5. So the chance they show odd number is 0.5. Okay. So 0.5 is the P here. All right. So the most important thing is you define the distribution with the right parameter. After that, will be easy. So binomial 8, 0.5. So come up odd number exactly 5 times. So that is asking P y equal to 5. Okay. So that will equal to, again, plug in the mass distribution function. Right. 1 minus P, so 1 minus 0.5, n minus x, 8 minus 5. So that is 0.2188. All right. So A and B has different distribution. So this is A. This is B for all number. Part C, find the mean number of the time a 6 come up. Okay, so they're asking for a mean value. And for mean value of binomial distribution, that is equal to NP. Okay. So mean equal to NP. Okay. And N is 8. P is 1/6. Okay. It's here, 1/6. D is asking the mean number, the time all number come up. Number of times all number comes up. So that is asking for mu y, again equal to NP. N is equal to 8, but P is equal to 0.5. Yeah. And E and F is asking for the standard deviation. Okay. Standard deviation is based on the variance. Okay. So the square root of NP times 1 minus P. So standard deviation of the time, number of times 6 come up. So that is sigma x NP 1 minus P. 8. P is 1/6. And F. Standard deviation number of times all number comes up. So that is sigma y. N is still 8, but P will be 0.5. Okay. All right, that is question number 6, and our last question for binomial distribution. Okay. Questions so far? All right, we have around 19 minutes. Let's look at section 4.3. on page 227. Here. First is question number 2. The number of pits in a corroded steel coupon follow a Poisson distribution. Okay. Tells us it follow a Poisson distribution with a mean of 6 pits per square root of centimeter. Square centimeter, sorry. And x is the number of pit in 1 centimeter square area. Okay. So follow Poisson distribution. For Poisson distribution, it has only one parameter, which is lambda. Okay. So let's write down the px lambda to the power of x over factor of x. The mean value, lambda, the variance, lambda. Okay. So x will follow a Poisson distribution. Okay. So the question is asking x is number of pit in 1 centimeter square area. Okay. And the mean value for that 1 centimeter square is 6 pits. So lambda will equal to 6. So x follow, not equals. So x follow Poisson 6. Okay. So p x equal to 8 will equal to here. We just plug in the equation here. So e to the power of negative lambda, negative 6. Okay. So lambda is 6, x is 8, okay. And x is 8, so factor of x. Okay. So we plug in number here. It shows us. So 10% of the chance we have 8 pits in 1 square centimeter area. That is part A. So part B is the same. So px equal to 2, you just plug x equal to 2 into that mass function. Lambda still 6. Okay, I will skip the details. Okay, for C, x less than 3. Okay, so x less than 3, that is equal to p x equal to 0. So don't forget this. Okay, so x could be 0 plus px equal to 1 plus px equal to 2. Okay, so that's less than 3. So again, don't forget x equal to 0. So that is possible. That's part C. Part D. Okay. So D is asking px larger than 1. All right. So x, remember, is number of pits in a 1 square centimeter area. Okay. So that number of pits could be, larger than 1 could be 2, 3, 4, 5, 6, 7, 8, 9, 10, or even 100. Okay. So even though the higher the number of x, the chance is smaller, because based on this mass function. Okay. The chance is much smaller, but that's possible. Okay. So for this question, we can use, again, because all the possible outcomes added together equal to 100%. So Px larger than 1 is equal to 1 minus Px equal to 0 minus Px equal to 1. Okay. Part E is asking the mean value. So mean value is equal to lambda. That's true for all the Poisson distribution. And the lambda is 6. So F. Yes, F is asking the standard deviation, sigma x. Okay. So sigma x is equal to square root of lambda. Okay, don't forget. So that's the variance. So sigma x squared equal to lambda. So for sigma x is called standard deviation. Sigma x squared is called variance. Okay, so pay attention to this. That's the square root of lambda, square root of 6. Okay. Well, so that is question number 2. Okay, so let's do the next question. Question number 6 as our last question for today's class. All right. Okay. Question number 6. Right. So 1 out of every 5,000 individuals in a population carries a certain defective gene. And we have random sample of 1,000 individual is studied. Okay. So part A, what is probability that exactly one of the sample individual carry the gene? Okay. So if we define X is the number of individual carry the gene, that's what the question is asking. Okay. And X is the number of 1,000 Bernoulli trial, because we can think this experiment as 1,000 Bernoulli trial. So a sample of 1,000 individual, and for each individual, the chance he or she carry a gene is 1 over 5,000. Okay, so it is, so X number of people in a sample carry that defective gene. Okay. So N is 1,000. So we have 1,000 Bernoulli trial. Okay. And for each one of these people, the success probability is 1 over 5,000. One over 5,000, it is 0.0002. Okay. Okay. So this is a Bernoulli trial. N is equal to 1,000, P is equal to 0.002. Okay. And because N is very large and P is very, very small. Okay. So N times P is equal to 1,000 times 0.0002. So that is 0.2. Okay, so n large and p small. Okay, so we can use Poisson distribution to describe that. Okay, so lambda is equal to np, which is 0.2. Okay, so we can use Poisson distribution 0.2 to do the calculation. A, what is property that exactly one of the sample individuals carry the gene? Okay, so that is equal to px equal to 1. Okay, so plug in the Poisson distribution function. So E lambda is 0.2, x equal to 1 over 1 factorial of 1. Okay, 1637. B, the property of none of the sample individual carry the gene. Okay, so that is asking p x equal to 0. So 0 people carry the gene. Okay, if you skip the details. So right now x equal to 0, lambda is still 0.2. C, property that more than 2 of the sample individual carry the gene. Okay, so that's asking px larger than 2. Okay, again, we do not do that directly because x could be 3 or 4 or 5, 6, 7, 8, 9, 10, or even 100. Okay, so you cannot do the direct calculation. So we use, based on the truth, all the property added together is equal to 1. So px larger than 2 is equal to 1 minus px less or equal to 2. Okay, so don't forget the equality line. So that is equal to 1 minus px equal to 0. Don't forget x could be 0. Minus x equal to 1 minus x equal to 2. Okay. All right. Again, pay attention to the equality line here. D, what is the mean of number of sample individual carry the gene? So that is the mean number, mean value. Because x follow Poisson 0.2, mean value will be equal to lambda equal to 0.2. F, what is the standard deviation? Again, standard deviation is equal to square root of lambda square root of 0.2. Okay. All right, so let's stop it here for today. We have one more lecture Thursday this week.